Okay, the last section, part 8, is on chapter 19, acids and bases. 79. 79 is basically having you fill out a table about some things that we know about acids and bases. For instance, how they taste, sour, bitter, how they feel, the pH range. Remember, 7 is neutral, so anything below 7 is acidic. Anything above 7, from 8 to 14, is going to be a basic solution. Acids have more H's, hydroxides, or bases have more hydroxides or OH's. You can see how they end. The word alkaline is associated with base. In phenolphthalein, acids are clear, so are neutral solutions for that matter, and they only turn pink in medium to strong bases. And then if you use the universal indicator, it's normally green. However, if it's in an acidic solution, it's in the Roy side, red, orange, or yellow, and if it's in the basic side, it's in the blue, indigo, violet side. Now, normally we look to see if something's a base. We look to see if they have OHs. Ammonia, if you look at the formula, it doesn't have OHs, but according to the Bronsted-Lowry definition, NH3 ends up picking up or accepting hydrogen ions and becoming NH4 with a +1 charge, and that makes it an acceptor, so that makes it a base. And as a result, it creates in the solution hydroxide ions. So it doesn't officially have hydroxides in its formula or in its molecule, but it ultimately produces these same hydroxide ions that all bases do. Number 81, imagine you have a strong base you need to neutralize. Explain how you would do this. Well, if you have a strong base, get a strong acid. And put the two together. The H's from the acid are going to combine with the OH's from the base. And if you take an H and an OH, you put them together, you get H2O. You get water. So the H's and the OH's will cancel each other out, make water, and then you'll end up with a pH of 7. You'll also produce a salt. Neutralization reactions end up producing a bunch of water molecules and a bunch of salt molecules from the leftovers. And finally, last question here, number 82. It says, imagine a substance dissociates completely into positive cations and OH ions. Is this a strong acid, strong base, or a weak base? Well, right away we know that it's a base because of the OH. And then it says it dissociates completely. So that means that the OH is whatever it's bonded to, the cation. Let's imagine that it's X bonded to OH. We'll do two examples here and explain this. X bonded to OH, and then here let's take a look at a different substance, a made-up one here, and it's Y bonded to OH. So we put this in solution, and according to our question here, it says it completely dissociates. So that means we end up with X's and the OH over here. They separate. And over here, another X, and another OH, and another X, another OH. They're all separate from each other. Versus over here, let's drop in Y and OH. We drop in YOH and we still get YOH. We still get YOH. We still get YOH. And maybe only one separates. This, because they all separate, or most of them separate, this is considered a strong, and because it's OH, it's a strong base. And this one, because not many separate, it's a very weak base. We only have, in this case, one set of OHs, and the rest are all staying together. So this would be a weak base. Okay. And then the second question said, what would a weak acid do in solution? Weak acids would just separate into the H's, but because it's weak, not many would separate into H's. So we might put, I don't know, maybe HF in there. And we drop them in, and maybe one separates, but a lot of them stay together. HF, 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 you get the idea. So because very few separate, it's considered weak. Oops, weak. Alright, so there you go. You're all done. You've got all the sections. Hopefully you'll study and do really well on the test. Good luck.